हेलो दोस्तों, वेलकम टू टुडेज मैथमेटिकल वॉक थ्रू। आज हम एक बहुत ही क्रूशियल थ्योरम पर डीप डाइव करने वाले हैं, रीमन स्टिल्टजेस इंटीग्रेबिलिटी। स्पेसिफिकली जब हम उसे एक कांस्टेंट से मल्टीप्लाई करते हैं। यू माइट बी वंडरिंग, अगर हम किसी फंक्शन को एक कांस्टेंट से स्केल कर दें तो क्या उसकी इंटीग्रेबिलिटी रूइन हो जाती है? वेल, एब्सोल्युटली नॉट। और आज हम बिल्कुल नोट्स के स्टेप बाय स्टेप फ्लो को फॉलो करके इसे रिगरसली प्रूफ करेंगे। सो लेट्स गेट राइट इनटू इट।
Here is our quick roadmap for today's session. 1. Theorem and its meaning. 2. Notations and proof idea. 3. Proof case I for a positive constant. 4. Proof case 2 for a negative constant. 5. Case 3 and conclusion. And finally, 6. Important points and formulas.
All right, starting right off with section 1, theorem and its meaning.
Let's look at the exact mathematical statement. Theorem. If f belongs to R of alpha on the interval AB and C is a constant, show that CF belongs to R of alpha on AB and the integral of CF d alpha equals C times the integral of F d alpha.
So simple words में इसका मतलब क्या है? It just means that if f is Riemann-Stieltjes integrable with respect to alpha, then multiplying by a constant C does not affect its integrability at all. और सबसे handy part, the constant can literally be taken outside the integral. As you can see, the integral of CF d alpha equals C times the integral of F d alpha.
Moving right along to section 2, notations and proof idea.
Before building the house, we need our tools. Let's set up our key notations. P is our partition of AB, where A equals x0, which is less than x1, all the way up to xn equals b. Delta I is alpha xi minus 1, which is greater than or equal to 0 since alpha is increasing. Mi is the supremum of f, and mi is the infimum of f on the subinterval xi minus 1, xi. Up f alpha is the upper sum, which is the sum of mi delta I. Lp f alpha is the lower sum, which is the sum of mi delta I. And crucially, our core integrability condition, f belongs to R alpha if and only if for all epsilon greater than 0, there exists a partition P such that UPF alpha minus LPF alpha is strictly less than epsilon.
अब आते हैं हमारे battle plan पर, the idea of the proof. The strategy is to first compare the sup and inf of CF on each subinterval with those of F. Then we show that UP CF alpha minus LP CF alpha equals the absolute value of C times the difference UP F alpha minus LP F alpha. Next, we use the integrability of F to conclude the integrability of CF. And finally, we just pass to the limit as the mesh goes to 0 to nail down that exact integral formula.
Okay, section 3, proof case I, positive constant. Let's tackle our very first scenario.
Step 1. We take any partition P of the interval AB. For each I, let mi equal sup f and mi equal inf f. Now, since C is strictly greater than 0, things behave very predictably. The sup of CF simply equals C times sup f, and the inf of CF equals C times inf f. This directly implies that mi of CF equals CMI, and mi of CF equals CMI. Pretty straightforward, right?
Step 2. इसका हमारे अपर और लोअर सम्स पर क्या इफेक्ट पड़ता है? वेल, UP, CF, alpha equals the sum of MI, CF delta alpha, which is the sum of CMI delta alpha, giving us C times UP, F, alpha. Similarly, for the lower sum, LP, CF, alpha equals the sum of MI, CF delta alpha. Factor out the constant and we get C times LP, F, alpha. Notice how beautifully that constant C just slides right out of the summation.
Step 3. Let's find the difference of those upper and lower sums. Subtracting them, we clearly see U of P, C, alpha minus L of P, C, alpha equals C times the bracketed difference, U of P, F, alpha minus L of P, F, alpha.
Step 4. Let epsilon greater than 0. Since f already belongs to R alpha, we can strategically choose a partition P such that U of P, F, and alpha minus L of P, F, and alpha is strictly less than epsilon over C. Plugging this back into our difference equation from step 3, U of P, CF, and alpha minus L of P, CF, and alpha equals C times that difference, which is now strictly less than C times epsilon over C. The c's brilliantly cancel out, leaving us with exactly epsilon. Hence, CF belongs to R alpha for C greater than 0. Boom! Case I is officially proved.
Let's shift gears now. Section 4, proof case 2, negative constant.
Step 1. You throw a tricky here, so pay close attention. Let C equal negative D where D is greater than 0. Then CF equals negative DF. Here's the real game changer. Multiplying by a negative number reverses the order of supremum and infimum. So the sup of negative df actually equals negative d times the inf of f. And the inf of negative df equals negative d times the sup of f. Substitute c back in, and this implies MICF equals CMI and MICF equals CMI. Did you catch that? They completely swapped.
Step 2, let's see how this swap messes with our sums. The upper sum UPCF alpha equals the sum of MICF delta alpha, which is the sum of CMI delta alpha, which evaluates to C times LPF alpha. And the lower sum LPCF alpha becomes the sum of CMI delta alpha, which evaluates to C times UPF alpha. Because of the negative sign, the upper sum of CF is literally tied to the lower sum of F and vice versa.
Step 3. Let's take the difference now. UPCF alpha minus LPCF alpha equals C times LPF alpha minus UPF alpha. But we want this in standard form. By flipping the terms inside the bracket to make it upper minus lower, that C becomes its absolute value. So it exactly equals the absolute value of C times UPF alpha minus LPF alpha.
Step 4. Almost there. Let epsilon greater than 0. We choose P such that U of PF alpha minus L of PF alpha is strictly less than epsilon over the absolute value of C. Now looking at our difference, U of PCF alpha minus L of PCF alpha equals the absolute value of C times that difference, which is less than the absolute value of C times epsilon over the absolute value of C. Once again, it perfectly cancels out to equal epsilon. Hence, CF belongs to R of alpha for C less than 0. Case 2 is handled.
Now for the simplest part, Section 5, Case 3, and conclusion.
For case 3, we simply have C equals 0. If C is 0, then CF is just the 0 function. The 0 function is trivially Riemann-Stieltjes integrable, and the integral from a to b of 0 d alpha equals 0, which obviously equals 0 times the integral from a to b of f d alpha.
Step 5. Checking the integral formula across the board. For C greater than 0, the integral of CF d alpha equals the infimum over P of UPCF alpha. This equals the inf of C UPF alpha. Since C is positive, we just pull it out. C times the inf of UPF alpha, leaving us precisely with C times the integral of f d alpha. For C less than 0, using CF equals minus df, the integral of CF d alpha equals the integral of minus df d alpha, which is minus d times the integral of f d alpha. Substitute C back, and we get C times the integral of f d alpha. And for C equals 0, as we just established, both sides are 0.
Which brings us to our ultimate conclusion. For all constant C, whether positive, negative, or 0, CF belongs to R alpha on the interval a to b, and the integral from a to b of CF d alpha exactly equals C times the integral from a to b of f d alpha. The theorem is flawlessly proved. Section 6. Important points and formulas. Let's do a quick wrap-up to solidify this in your mind.
Here are the critical takeaways to remember for your exams. Number 1, for C greater than 0, the order stays exactly the same. Sup CF equals C sup F. Inf CF equals C inf F. Number 2, for C less than 0, the order reverses. Sup CF equals C inf F, and inf CF equals C sup F. Number 3, the difference formula always uses the absolute value. UPF CF alpha minus LPF CF alpha equals the absolute value of C times UPF F alpha minus LPF F alpha. Number 4, we use the integrability of F to control that final difference by epsilon. And number 5, the constant always comfortably comes outside the integral.
Finally, here are the key formulas one last time. The upper sum UPCF alpha is the sum of mi of CF delta alpha I. The lower sum, LPCF alpha, is the sum of mi of CF delta alpha I. Their difference is the absolute value of C times the difference of the upper and lower sums for F. And of course, the grand finale, the integral from a to b of CF d alpha equals C times the integral from a to b of F d alpha. I highly recommend you practice writing this proof out step by step on your own. Now, before we sign off, I'll leave you with a provocative thought. What if C wasn't a static constant, but a dynamically changing variable function? Do you think this smooth integrability would still effortlessly hold up? Think about it. Thanks for joining me on this mathematical walkthrough, and keep exploring.